This is just a short concept bite, continuing on with our theme of errors in values on the propagation of errors. So how we go from having an error in a measured value to how we go to having an error or an uncertainty in a calculated value. So previously I've explained how we get from our measurements to our sample standard deviation and then to our value of the standard error of the mean. From now on, I'm just going to refer to this value as either the error or the uncertainty. And I've also said that you'd expect the more measurements you make of something, the more confident you are in this value. This is where this value of standard deviation relates to the standard error of the mean. Now, there's always going to be a limit on how well we can measure something. And consequently, there always has to be a limit on how well we can calculate something. And it's getting between the two that is the focus of this video. Just like when we have significant figures, we have different rules for the method of our calculation. So I'm going to start off with the rule for addition and subtraction. When combining errors of addition and subtraction, in the simplest case, I can get a maximum value for the uncertainty by just going with simple addition of the uncertainties in every step of the calculation. This actually overestimates the uncertainty, and a better measure of the uncertainty is given by the equations on this page. Here, if I take the sum of the squares of the uncertainty, that would give me the square of the uncertainty of my calculated value. Putting that into practice, here is an example of determining the limiting molar conductivity of a weak electrolyte based on calculations because of measurements in the limiting molar conductivity of strong electrolytes. It's very difficult to measure the limiting molar conductivity of a weak electrolyte directly, so this is actually our best method of going about it. I can imagine that I've recorded the limiting molar conductivity of each of my strong electrolytes in each case and given each of them the uncertainty associated with their measurements. If I want to work out the limiting molar conductivity of my acetic acid, my HAC, I can just do a simple calculation, as shown above, giving me this value of 390.6 Siemens centimetre squared per mole. For my propagation of my uncertainty, I could just go with the simple option of adding all of the values of the uncertainty up, or I could go with the slightly more detailed version using this version of the error calculation. In this case, I have an uncertainty of 0.8 in my sodium acetate, 0.9 in my HCl, and 0.8 in my sodium chloride. Just going back, you'll remember that the errors presented in brackets are an uncertainty of the value in the bracket in the number immediately preceding the bracket. If I sum the squares of each of these values, I end up with 2.09, and I take the square root of that, I end up with something around 1.45, which always gets rounded up, so my uncertainty becomes 2. This means that I need to round my value for my limiting molar conductivity of my acetic acid to reduce the number of significant figures. If the uncertainty is in the number immediately before the decimal place, there is little point in me reporting the number after the decimal place. So I've reduced my answer from 4 significant figures to 3. In the case of calculations where I'm multiplying or dividing, then I have a different equation that I need to use. Simply put, I can work out the fractional uncertainties of each of my values and sum these and calculate my uncertainty in my calculated value accordingly. Just with before, this gives me my maximum value. It's the rough, quick estimate. A better way of calculating the uncertainty is using a similar approach, taking the squares of each of these values and then taking the square root of the total. So this calculation is based on determining the concentration and the uncertainty in their concentration of a solution which has been made up from 20 milligrams of a solid dissolved in 5 millilitres of aqueous solution. Now, I've given my molar masses and their uncertainty, and I've given the uncertainty on the mass and the volume. We should know the two simple calculations for moles. Moles is concentration times volume, and moles is mass over the molecular mass. And a little bit of algebra helps me combine these into a single equation and rearrange it for the concentration. It's far better to combine equations into a single equation and only calculate the uncertainty once than try to propagate it through multiple steps in a calculation that could have been avoided just for the sake of a small amount of algebra. Now, in this case, just substituting my numbers in, I can then calculate my concentration, which comes out to the appropriate number of significant figures as 31 millimolar. So, looking at the uncertainty in this case, I need to know my calculated value of my concentration. And just remember that this is an equation where I've had multiplication. Now, technically, that RMM term is combined by the sum of all of these things. So I can't quite use this equation I've got here in the first instance. So if I just use the basic, very simple version, just to very quickly calculate the uncertainty, what we'll find is that the uncertainty on the molecular mass is completely negligible when compared to either the uncertainty on the volume, and that uncertainty on the volume is very small compared to the uncertainty on the mass. Ultimately, I get the same answer whether I ignore these latter two terms or whether I include them. So I can simplify this equation to just include the uncertainty on the mass term, because that 1 in 20 uncertainty of the mass is so huge. And when I calculate this value, this gives me an uncertainty of 2. Again, I've rounded up to only have one significant figure. And so my calculated value of concentration is 31 millimolar plus or minus 2. So just in summary, I use a different method on combining errors, whether I am using addition or subtraction or multiplication and division. And I can have simpler or more complicated versions of the equation depending on how much detail I need to know it. Squaring the terms enables me to minimise the effect of smaller terms so that I don't even need to include them in the calculation, often making it a much faster process. I hope this video has been helpful. I'll be back with more.